So to finish off the notes, in this unit we talked about metathesis, which was precipitation reactions. We talked about acid-base neutralization. And we talked about redox. The biggest type of redox reaction is the ion-electron balancing, which has many, many steps. So we're going to talk about some other reactions. A lot of these are going to seem familiar. These are also redox reactions because there is oxidation and reduction taking place, but they're not as complicated as the ion-electron method. So let's go through them. So we talked about synthesis. Also known as combination or direct combination. And so this is a fairly simple type of reaction that whenever you have two elements that are going to react, the only thing two elements can really do is bond and combine, right? And so it could be a metal with a nonmetal, or it could be a nonmetal with a nonmetal. So calcium, which you would simply write as Ca, reacts with air. Whenever they say react with air, the implication is it's oxygen, because oxygen is the reactive component of air. So calcium plus oxygen. Remember that oxygen is one of the diatomic elements. So if these two elements are going to react, the only thing that they can do is combine. So in order to combine them, you just need to know what charges they have so you write the formula correctly. So calcium is an alkaline earth metal. You know that's going to be +2. Oxygen is -2. So when they come together, a +2 and a -2 form CaO, calcium oxide. And now it's just a matter of balancing. Well, you've got two oxygens, so put a 2 here. That gives you two calciums, so put a 2 here. And now you're done. I forgot to write in the states here. So the solid metals by themselves are always solid, except for mercury. Oxygen is a gas. And the ionic compounds, guys, remember, are always solids. Okay, let's try another one. Iron metal is heated in the presence of chlorine. All right, so chlorine is another diatomic element. The other thing you should know about chlorine from the periodic table is that it's color-coded red. What does that mean? If the element is red on the periodic table, what does that mean? It's a gas, yes. So Fe, solid, plus Cl2, gas. Now, here there's two possible outcomes because iron is multivalent. It could be +2 or +3. Either one is acceptable. Generally speaking, when the reaction happens, it first forms FeCl2 and then can be further oxidized to form FeCl3, but if you put either one, it's fine. So we could write Fe, let's say it's just a charge of +2. Chlorines have a charge of -1, so let's say that is the compound that forms. And the balancing, that's all the balancing I need to do there. Solid sodium. So sodium placed in hydrogen gas. So hydrogen is also a diatomic element. It's also a gas. Okay, so when you look up the charges, alkali metals can only be +1. And hydrogen, you are used to seeing hydrogen as +1. But when hydrogen is combined with metals, hydrogen will be negatively charged. And that's pretty much the only time you're going to see hydrogen negatively charged. So this is sodium hydride. Remember the oxidation numbers rules, right? How the rule for hydrogen was rule 6, but the rule for alkaline metals was rule 5. The more important rule is the lower number. So it's more important that sodium is +1 than hydrogen. So now we balance, put a 2 here, put a 2 here, and it's a solid. Okay, now sometimes when you have nonmetals reacting with nonmetals, it gets a little murky because the nonmetals, remember we did that example with nitrogen where it had pretty much every single oxidation number possible, right? So nonmetals, because they can vary so much, there's lots of possibilities. So if we said, oh, oxygen gas reacts with nitrogen gas, you could write many different possible products, and they would all be valid because they're all technically possible. NO, N2O, NO2, N2O3, N2O5, N2O4, all like lots of possibilities. So nothing would be wrong because of nitrogen's many charges. Okay? So, any questions about synthesis reactions? Very straightforward. If you can write a formula from two elements, then you can do a synthesis reaction. Okay? Single replacement. A single replacement reaction is simply when you have an element plus a compound. An element plus a compound will give you an element plus a compound. So, aluminum is placed in an aqueous solution of copper 2 sulfate. So you would write this as Al plus CuSO4. They said a solution, so this is aqueous. So the thing with a single replacement is the way to predict what you're going to get is to look at what you're given. I was given a compound and a metal. The metal will displace the metal in the compound. Those are the two that are going to switch. But remember, you have to be aware of their charges so you write the formulas correctly. So what I'm saying is aluminum will go in, copper will come out. So copper comes out, and when I say come out, I mean be reduced and become solid form. And so now aluminum, which is a +3, and sulfate, which is a -2, we have to make this work. And now we worry about the balancing. So 2 aluminum, or 3 sulfates, 3 there. That means 3 coppers. That means 2 aluminums. Here is the balanced, and this is in solution, and sulfates are aqueous, mostly. So here's my molecular equation. But this is not, we're not done, because you need to know how to whittle down to the core of the reaction, meaning you need to know how to get to the net. So when I write this as everything as ions, 2 aluminum plus 3 copper 2 plus 3 SO4 2 minus forms 3 copper solid plus 2 Al plus 3 SO4 2 minus. What are my redundancies? What can be canceled? The sulfates. And so your final will be, or your net will be 2 aluminum plus 3 copper ions forms 3 copper solid plus 2 aluminum ions. This is a single replacement. One element goes in, one element comes out. And the other, there's a third ion, which is typically a spectator. If this is in solution, the third ion is going to be a spectator. All right. There's another way that this can happen. And the difference is, what if your element is a nonmetal? Well, if your element is a nonmetal, then the nonmetal goes in and the nonmetal comes out. So, chlorine gas, Cl2, is bubbled into an aqueous solution of potassium iodide. Your nonmetal goes in, your nonmetal comes out, so what is coming out? Yes, iodine. I2. And then I have KCl, aqueous. We balance this with a 2 here and a 2 here. Okay? This is how classically a single replacement looks like. We're in sophomore year, this is what they look like when we did this then. But as you now know, we need the net ionic equation. So can you tell without writing the middle step what's going to drop out? No, we need the Cl. Cl is actively being reduced. Yeah, the potassium. And can you also tell why this is a redox? All these examples I'm going over now are redox. All right, what was oxidized here? Iodine, yeah. Okay, single replacement. Element goes in, element comes out. Which one comes in, which one comes out? It depends on what the element is. Okay? All right. Metal reactivity. So there are metals that we call active metals. The active metals are groups 1 and 2. Alkali metals, lithium, sodium, potassium, rubidium, and earth metals, so magnesium, calcium, strontium, and so on. Now these are called active metals because they easily react with water and air. Okay, so what happens is, whatever the metal is, any one of the group 1 or group 2 metals, they're going to react with water, and you will get a metal hydroxide and hydrogen gas. Right? We did this. This was the first reaction in your lab yesterday. No, it wasn't. Just kidding. That was acid. But if we took a metal and we put it in water, you would get bubbles. The bubbles would be hydrogen gas. Right? It's just in your lab, it happened a lot faster because we use acid, but you would get hydrogen gas with water as well. It would just take a lot longer, and you wouldn't create enough to make that popping sound, but you'd still get some. So when you look at here, potassium reacting with metal. Here is the metal hydroxide. How come the metal hydroxide is not written together? It's soluble, and it's a strong base. A strong base is, you don't write them together. Right? You separate them out. And here's the hydrogen gas. Here's an earth metal, calcium, reacting with water. We get the calcium ion, hydrogen gas, and here's the hydroxide. It doesn't matter which order you put the products, as long as what you have is numerically balanced. So let's try one. Let me give you one and kind of just match the pattern here. Lithium. What's our product or products? What are we going to get? Yep, we're going to get lithium ion. H2. Hydroxide. Now you have to balance these. Oops. You have to balance these, so I don't have my hydrogens balanced, so let's throw 2 in here, which means I'm going to need 2 in front of here. Is that balanced? It may look like it is balanced, but it is not balanced according to Redox. Why? What is wrong about this that means that it is not balanced? What else has to be balanced? Charges. How do I balance the charge now? Yes, the 2 in front of the lithiums. Do you guys see that? Because you have 2 hydroxides on the right side, which is -1. So you need 2 positives to cancel the right side to make it neutral. We could have broken this apart and done this with the ion electron method, but generally you don't have to. This is not that complicated where you need to do that. But you could if you wanted to. Let's do another one. Magnesium with water. You know, maybe it's easier to look at it this way. What if I wrote the water this way? You can think of this like it's a single replacement, because the magnesium would displace the positive ion in the compound, which means hydrogens would come out. Does everyone see that? This is just like a single replacement. Okay, so we would get Mg2 positive, we would get hydroxides, we would get H2. And we would have to balance it, so we'd have to put a 2 there and 2 there. Except, my bad. This is unique. I actually wrote this incorrectly because this has to be written this way. How come? It is weak base, yes, and it's not soluble. And remember, if it's a solid, it is written together, not separate. So that's tricky, right? So when you're writing net equations, at the end of it, you should still be aware of your solubility rules and think to yourself, all right, did what I write make sense? Is this supposed to be in a solid form? Is this supposed to be aqueous? Okay. So metals, first two columns are active metals. They will react with water. You get hydrogen gas, and you get a metal hydroxide. Whether that metal hydroxide is solid or aqueous depends on the solubility rules. All right, so the last type is combustion reactions. And combustion reaction is fairly simple, meaning that it's always the same products. A hydrocarbon is a compound that contains mainly carbons and hydrogens. It might contain some oxygen too, right? And when we burn it, burning it means reacting with oxygen. So here I'm showing methane reacting with oxygen. The products are always the same. Carbon dioxide and water. The water is in liquid form. A lot of people think that the water you form is steam. When water is formed, it is formed in the liquid state first, but it might vaporize because there was so much heat involved. But when it's formed as liquid, okay? That's why there's an L there. So then you balance it. So this is just a matter of practicing balancing, which we did this back in the beginning of stoichiometry. So let's say we had something like C3H7OH. This is propanol. You always react it with oxygen. You always get CO2. There's a certain method to balancing combustion reactions to make it easier. What am I talking about? What's your approach? What should you do first? Carbons. Do the carbons, right? So 3 carbons on the left, so let's put a 3 here on the right. And then what? H's, yeah. So I've got 8 H's on the left. So to get 8 H's on the right, I put a 4 there. And so now count up your oxygens because that's the last thing you have. So we've got 3 times 2, we've got 6 O's here plus 4, so that's 10 O's on the right side. On the left side, you've got to make 10 O's out of what you see here. So if I put a 5 here, that would be 11. So 5 would not work. If I did 4.5, 4.5 times 2 is 9 plus 1, that is 10. But we generally don't use halves. We'd like to use integers in our balancing equations, which really means we double everything. All right, so that's combustion. That was definitely review. Okay, so these are some practice problems. We don't need to do these now. We'll just save those for later. So we've gone over all the reaction types. The worksheets that you picked up, worksheets 4 and 5, have the samples of every category split up. The answer keys are posted, so kind of work your way through those. Check yourself. Make sure you know how to do them. I do have more, okay, worksheets. Like this is just the tip of the iceberg because this is generally something that's kind of, people find it hard. So for tomorrow, the ASA on the hydrogen peroxide, that's our lab tomorrow, and that is the formal lab. Now, the formal lab, because we have a test on Wednesday, the formal lab is going to be due after the test. So you can focus on studying for the test until Wednesday, but the formal lab will be due on Thursday. I just figured it would be too much to have it due before the test. Okay? You'll see it. It's in Schoology. It'll tell you when it's due. All right, so use the time, work on those worksheets.